Good morning, all. I'm going to talk about the photodetector fabricated in my laboratory based on lead sulfide thin film on paper. This paper is basically a calcite paper which is used to print our visiting cards. So this is the cheapest method where we can deposit a good quality photodetector. So photodetectors are basically of three types: photoemissive, photovoltaic, and photoconductive type. And all these three types of photodetectors are used in commercial applications. So why I choose a lead sulfide isn't based on basically the content of that particular material. Lead sulfide is basically have a lower band gap, which is zero point 0.4 electron volt, and which is very good to sense IR radiation in that particular uh, energy range. So that's why we use lead sulfide as a photo detecting material. So experimental method is explained in this way, where I have synthesized these films, lead sulfide films, thin films on paper at 100 degrees centigrade, and these films were deposited by using spray pyrolysis method, which is shown in this slide. So after deposition, the film is analyzed by using structural and surface characterization methods like X-ray and SEM. X-ray diffraction shows polycrystalline nature of lead sulfide thin film, and SEM shows the film is totally covered on the surface of the paper. So this is basically the device setup which I have used, which consists of an 100-watt lamp. This is just a normal table lamp which do have a peak wavelength something around 800 nanometer, and a current source, basically a voltage source and a current meter. If you see the graph on the left hand side, bottom left hand side, it shows the graph of a photocurrent with applied voltage. The black line represents the dark current. The dark current is almost like stable, and it increases slowly with increasing the voltage, and it may be because of the defects which are present in that particular film. And as the light intensity increases, the photocurrent which is developed in that film is also increasing. So we can see that from 5 milliwatt to 320 milliwatt, we have varied the light intensity, and the photocurrent also increases in that particular range. The photosensitivity measurement we have did for that, we did in pulse measurement, where the light is turned on and off for 60 seconds. 60 seconds it is on and 60 seconds it is off, and I have measured the photocurrent which is developed across the device. What I found is that whenever I turn on the light, the photocurrent increases. Whenever I turn off the light, the photocurrent decreases, which indicate that this is a good reversible characteristics. The photocurrent increases as well as the photocurrent decreases. Real-time measurement will going to give you the fast or the recovery or the response of that photodetector to the radiation. So the response is very fast. The recovery time is almost like 7 millisecond, and the decay time is almost like 16 milliseconds. So the response time is really fast, 7 milliseconds. So in this way we can say that the photodetector is having a good fast response. So this is a simple method which we have presented in this work, where we can synthesize this photodetector using lead sulfide thin film on 300 GSM paper. And this photodetector do have an excellent photo response and photosensitive characteristics, as well as they do have a very fast detection speed, which is 7 millisecond for the rise and 16 millisecond for the decay. So this photodetector is basically produced by a simple and low cost method by using spray pyrolysis. Thank you.